4.1, increasing and decreasing functions. So let's recall, when reading a graph, we read it from the left to the right, just like when we read a book in English class. When we read a graph, and we want to determine whether the graph is increasing or decreasing, so that's the focus today, what we do is we focus on the y coordinates and whether the y coordinates are getting bigger or smaller, okay? If they're going up or if they're going down. Because when we have an x and a y axis and we're focusing on the y coordinates, what's happening is we're looking at these numbers, okay? The more down they go, that's that's like the smaller the number, and the more up they go, that's the bigger the number, okay? And as just a quick recall, let's go -8 is actually smaller than the number, say 2, because it has a negative sign on it. So just know as the further we go down, because this is kind of like a number line, right? Like this y-axis is kind of a number line. The further we go down, the smaller the number. Even if this, like the absolute value is bigger, it doesn't matter because there's a negative, it's a smaller number. Okay? So we determine the intervals where a function increases and decreases in order to understand the behavior of the function. Okay, we kind of want to know what's going on. So here's an overview of intervals of increase and decrease. A function is increasing on an interval if for any value of x, and then like x2, so if we have f at x1 and then f at x2 and we compare this, f at x1 is smaller and f at x2 is bigger, okay? And of course, we accept the understanding that x1 comes first and x2 comes after. They're like chronological, okay? So as long as they're chronological, which is x2 is greater than x1, and we sub them into the function, it's increasing. Now, a function f is decreasing on an interval if for any like chronological number, right? x1 is less than x2, so this is increasing the x values, right? We're going to the right, we're reading to the right. When we sub it in, f at x1 is greater than f at x2. That means that this coordinate is greater than this coordinate. That means we're falling. Okay, so example 1, examine the intervals of increase and decrease of the equation f at x equals x squared. Okay, so we have this polynomial x squared. This is going to be x squared, and then we're going to go, this is 1, this is -3. This is actually f at x equals x minus 1 squared minus 3. Okay, and then we're going to talk about the slopes of the tangents. Okay, so if we look at this function, we know that we have a turnaround point here when our tangent, the slope of the tangent is 0. Okay, so there's, this is called a critical point. So this is going to be a turnaround point, or this is going to be called a critical point. Okay, and that occurs at 1, -3. Okay, and this is going to be a potential max or min. But because we're not doing this algebraically and we're doing graphically, we can say that this is a turnaround point. Okay, so we read graphs from left to right. So if we start at the very left, what's going on here? Okay, we're going down, 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 down. We're starting at 8, 7, 6, 5, 4, 3, 2, 1, 0, -1, -2, -3. Okay, so we can say that we're decreasing on -∞ to 1. But we're not decreasing at 1 because exactly at 1, we're at rest. Okay, and if we think about decreasing, we're thinking about negative slopes. Okay, so let's tie those together. Slopes are negative. okay, also on negative infinity to 1. So those two things go together. Now, let's talk about increasing. Okay, so after we hit this critical point, we continue to read to the right, and these numbers are now increasing. We go from this -3 all the way up to infinity. So we look at the y values, but we quote our answer in x values. So our x value here, where we have the turnaround point, is 1. So we write it down, but we use the open bracket so that we don't include it. And all the way up to positive infinity, we're going to be increasing forever. And what we can see here is if we draw the tangent slopes, okay, the slopes are positive. Okay, and that's on 1 to infinity. And those two things go together. So then I want to just add to this turnaround point, because then we can make this connection too. So we're going to have this horizontal tangent. Because we talked about negative slopes, we talked about positive slopes. So let's go horizontal tangent. And what does that mean for the slope? Slope of 0. So here's our conclusion. For functions that are both continuous and differentiable, we can determine intervals of increasing and decreasing y values using the derivative of a function. So increasing on the graph, okay, so the graph is increasing when the slopes of the tangents are positive. So that means, like, of course, this is the derivative f prime at x when it's greater than 0, right? Because remember, f prime at x just means the slope. Slope, instantaneous rate of change, okay? And we're decreasing on the graph when the slopes of the tangents are negative. So f prime at x is less than 0. So example 2, use graphing software to graph the following functions, then estimate the values of x where the graph is increasing and decreasing. Okay, so I will make a little sketch of each, and then I'll put increasing, I'll put intervals, and then decreasing intervals. Okay, that is what the question is asking us. So let's go ahead and open Desmos, and let's graph x cubed plus 3x squared minus 2. Okay, so I'm going to, because we're only focusing on, because we're focusing on intervals of increase and decrease, I'm going to plot -2, 2 and 0, -2. We'll go -2, 2, and then 0, -2. Okay, and then on this graph, we're going to plot here and here, which are our turnaround points. And there we go. So, interval of increase. We're increasing this entire time from negative infinity all the way to -2. Not including either, because we can't ever reach infinity, and the -2, the slope is 0. Okay, and then we start to decrease. So we decrease on -2 to 0. And then we increase again on 0 to infinity. Okay, now we have x over x squared plus 1. If we bring up Desmos, we can do x over x squared plus 1. Okay, I'm going to go ahead and change the y-axis. There we go. Okay, so we can see on here we're decreasing until -1, -0.5. Okay, so let's graph that. It's going to be -1, and there's going to be -1/2, and we're decreasing until about here. And then we're going to increase until this turnaround point, 1, 0.5, because we're going up. Okay, so that's turnaround point. It goes to 0. So this is 1, and then 1/2. And then decreasing again. Okay, and I'll taper off. So we can say that we're increasing on -1 to 1, and we're decreasing -∞ to -1, and 1 to infinity. So as a note, x-intercepts on the graph of f prime at x translates to a change in sign on the graph of f at x. Okay, from positive to negative or negative to positive. Okay, another point is this indicates that the graph is changing from increasing to decreasing. Okay, so now what we're going to do is we're going to take a look at the graph of f prime at x, which we have right here. And what we're going to do is we need to consider the graph of f at x. Okay, so what we're going to do is we're going to talk about what's happening in this graph and then what would have happened in the original. Okay, so as a note, and like to expand from here, when f prime at x, aka the slope, is greater than 0, from the two questions that we just did, the graph is, so in other words, a positive number, the graph is increasing. Or rising. Okay, so and obviously we regress left to right, so obviously rising to the right. Okay, and then another note just from like what we just did, so when that slope is less than 0, right, so in other words negative, the graph is decreasing or falling. So when we read this first point right here, and we see that the x-intercepts on the graph of the derivative, so these two x-intercepts here, what they mean is that there's a change in the sign. So that means we're going from positive to negative or negative to positive. So what we can see on here is there's going to be a change in sign. In other words, a max or min at x equals, and this is going to be approximate, let's go -0.5, just for simplicity. Okay, and then also at almost approximately 3. So there's going to be two changes in decreasing to increasing or increasing to decreasing. Okay, and just throwing this out there, so if we're going from increasing to decreasing, that means we're going up first and then we're going down. There's going to be a max. And if we're going from decreasing to increasing, so decreasing is going down first to increasing, what that means is that we're going to have a minimum. So taking a look at the graph, if we take a look at this arm right here, this arm is all above 0. Okay, so obviously the x-intercept is the cutoff of 0. So 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, and so on. Okay, so this is all positive. What that means is that we're increasing. Okay, so why don't we do a little bit of so f at x, and then we're going to compare it with f prime at x. Okay, so on the interval, the original interval of negative infinity to negative 0.5, what's happening on f prime at x is it's positive. What that means on f at x is it's increasing on that same interval. You know what? I know what I'm going to do. Here we go. Let's go negative infinity to negative 0.5. Okay, so it's positive numbers or positive y values. Okay, but on our original, it would be increasing. Okay, and then at 0, we know that that's going to be a maximum on the original, which is an x-intercept on the derivative. So what's going to happen here is we're going to go up and up and up and up. Okay, and we're going to have some maximum. We don't know, we haven't determined where that maximum is going to be. I graphed this before, so I know it's right here, but we're going to get further into the graphing. This is just the introduction. Okay, now the next interval. The next interval is going to be from 0 to 3. Okay, because the f at x values are all negative, right? They're below the x-axis. So negative numbers or negative y values. So what's going to happen is the original is going to be decreasing. Okay, so our turnaround point is, but then I want to blend this with the value 3. This is going to be a minimum. Okay, because on the derivative function, there's an x-intercept. So as soon as you see an x-intercept, okay, there's going to be a minimum. But we know that if we're going from increasing to decreasing, that's the max, and decreasing to increasing, that's the min. Okay, and then the last interval is going to be from 3 to infinity. And on the graph that we're given, which is f prime at x, the derivative graph, these numbers are all positive. So we can say positive numbers or positive y values. So what's happening here is it's going to be increasing. Okay, and obviously, and I'm going to highlight this in a different color, between an increasing going to a decreasing, there's going to be a max. And between a decreasing going to an increasing, there's going to be a min. So this purple graph right here represents approximately what's going on in our original graph f at x. And just as a reminder, this is going to be a cubic function, right? So example, this is going to be cubic, so x cubed, right? If we're talking about y prime, that's like, for example, 3x squared. So if our original is cubic, our derivative of a cubic is going to be a parabola, so quadratic. Right? We're going from degree 3 to degree 2. So if the function that they give us is f prime at x and they give us degree 2, our original was degree 3. You got to think forward, but you also have to think backwards. So all we covered today was intervals of increasing and decreasing, when we get a max versus when we get a min, right? Increasing on the one side, decreasing on the other, or decreasing on one side, increasing on the other. And then what a turnaround point means is that the derivative is 0, giving us our x-intercept, right? Derivative 0 here gives us our x-intercept on our derivative graph. On the original, the derivative is 0, giving us, again, x-intercept on our derivative graph.